Hey everyone, in this video we're just going to review a little bit about Riemann sums and using the definition of the definite integral. So I put some useful formulas here, the things that come up, the sums that you need to know their formulas in order to then evaluate the Riemann sum. So their first example, use Riemann sums. And what I mean by that is the definition of the definite integral to find the exact area. So we're no longer doing approximation, so we find the exact area represented by this integral. And so the definition of the integral to remember here is that the integral, when you're given the integral from a to b of f of x dx, this is defined to be the limit as n goes to infinity, where n represents the number of rectangles of our sum that we learned, that gives us without the limit, this is giving us just the approximation of the area. So it's I equals 1 to n of the area of each rectangle. So it's the base of the rectangle times the height of the rectangle. And usually that we denoted it as x of I star. So that's the base and the height, and then you sum the number of rectangles. So when we were doing approximations, we were doing 4 rectangles, 6 rectangles, 16 rectangles. Now we're saying, what if the number of rectangles goes to infinity? Then that gives you the exact area of under the curve. So this is the exact area, which is denoted by the integral from a to b. And so this is called a definite integral when it has the limits of integration, the a to b. So here we want to be able to then write the Riemann sum like this for this integral and evaluate it, because that represents the area, the exact area under the curve. So we need to figure out, okay, what is our delta x going to be? So I know delta x is the length of the interval, so b minus a divided by the number of rectangles we're using, which is n. So in this case, b minus a, what's a? A is 2 and b is 5. So b minus a will be 5 minus 2 over n. Right, we don't have a specified number of rectangles, so we just leave it as n. So the length of each rectangle is going to be 3 over n. So the base is going to be 3 over n. And then our x of I star is not specified. We're not told use the left rectangle or the left endpoint, the right endpoint, or the midpoint. So here you can choose which one you use. So you have the option. And so remember, the right endpoint, how do you find the right endpoint? And then how about the left endpoint, and what about the midpoint? Normally what I do is I break up the number line. So I break up the interval on a number line. So I'll put 2 and then 5. And so when I don't need to graph the function, but I just need to know that, okay, so my delta x is 3 over n. So if I just add my delta x, I'm going to get my next one. So this will be 2 plus 3 over n. And then that will be for the first rectangle. So this is delta x1 and then delta x2. They're all the same, right? But I'm just indicating the so 1 and so 2 to indicate the rectangle. So this is my second rectangle, so this will be add 3 over n again. So this is 2 plus 3 over n plus 3 over n, so that will be 6 over n, and so on. 2 plus then another 3 over n, so 9 over n. And if you continue in this manner, eventually you're going to get to your ith rectangle. It looks like a V rectangle. And so the question is, okay, so that's the one we're focusing on. We're adding 3 over n every time. So notice that when it's the first rectangle, it's 2 plus 3n. When it's the second rectangle, this is really 2 plus what? So this is really 2 plus 2, 3 over n, right? Or delta x. And this is 2 plus 3, 3 over n, and so on. So this is going to be 2 plus I, 3 over n, until you get to your 2 plus n times 3 over n, which will just be 2 plus 3, which is 5. or other endpoint. And so you're really focusing on the ith rectangle. And so the one over here will be then, this will be the left endpoint, and this will be the right endpoint. So the left endpoint is 2 plus, instead of I, 3 over n is the one before, so this will be 2 plus I minus 1 times your delta x. And so when you see the formulas in the book, hopefully then you see that from breaking up the interval, we get the formulas, right? So it's your a plus I delta x is your right endpoint. That will be this one. So in our case is a is 2, so it'll be 2 plus I times 3 over n, right? A plus I delta x. So 2 plus and then 3i over n, just simplify that. Our left endpoint will be a plus, and then the one before, I minus 1 times delta x. So in our case, 2 plus I minus 1 times 3 over n. And then we can simplify that. And the midpoint is your right endpoint plus your left endpoint divided by 2. So find those, and it's the midpoint of that. Usually that's the harder way of doing things. So which one is the easier one? If you have the one that has a choice, choose the right endpoint, because that one is the simplest one, because it's just a plus I delta x. You don't have all this other things like to remember, oh, I minus 1 times delta x, or finding the midpoint of that. If you do the math on this, right, the right endpoint plus the left endpoint divided by 2, then when you do that, what you should get is that your midpoint is going to be a plus I delta x. So it looks like the right endpoint, but then minus delta x over 2. So half delta x. So that will be your midpoint. So you can see how then, okay, these ones look a little bit more complicated. So unless you're specifically told, use the left endpoint or use the midpoint. If you have the choice, if it's not specified, if it just says use Riemann sums to find the exact area, me personally, I will choose the right endpoint because that's the simpler of the endpoints to use. And so let's try it. So now I already know. Let's put it all together then. So I want to be able to write my exact area. So the integral from 2 to 5 of the function, so which was 2x plus 5, as a Riemann sum, right? I want to find the exact area under the curve. So this gives us the area under the curve and above the x-axis. And so the things that we need are a, our b, and our function. So we already know a is 5. Oh, sorry, a is 2, b is 5. A is 2, b is 5. What's our function? Our function is whatever's in here, right? Looking at the definition, it says the integral from a to b of f of x dx is this, where, so our f is whatever's in here. So before the dx, after the integral symbol, the summa symbol, and then the dx. So our f of x in this case is 2x plus 5. We already calculated our delta x is b minus a over n. So delta x is 3 over n. And we are going to choose to use the right endpoint. So our x of I star, we're going to choose as the right endpoint, which we said in this case it is 2 plus 3i over n. So those are the factors to find in order to write the Riemann sum. So 2 plus 3i over n. And so now I can say, okay, so we're ready to write our Riemann sum and then evaluate it. So the integral from 2 to 5 of 2x plus 5 dx then is going to be the limit as n goes to infinity, the number of rectangles goes to infinity, of the summation I equals 1 to n of my delta x, so 3 over n, times f of my x of I star. We chose the right endpoint, so f of 2 plus 3i over n. And now I evaluate my right endpoint into my function. So f of that, and this is my f. So this is going to become limit as n goes to infinity of I equals 1 to n, 3 over n times, now I'm going to plug in my f into this. So let me use brackets, so 2x, so 2, and then my x is, instead of x, we're going to plug in 2 plus 3i over n, right? That is in place of my x. So this is our x of I star. And so I'm going to say 2 times x, so 2 plus 3i over n, and then plus 5. And when we evaluate a Riemann sum, so one of the first things is write the Riemann sum and then evaluate the function, right? Evaluate your endpoint that you're using. In this case, we're using the right endpoint. Evaluate it into the function. And our goal is to simplify enough that Riemann sum so we can use these formulas. We want to be able to get rid of anything that has a summation with an I and be able to change it into one of these so that we can take the limit. So right now I see, okay, I have this, so let's multiply it all out because my goal is to be able to take the limit. So I need to first get rid of my summation. So let's simplify as much as we can. So the limit as n goes to infinity of the summation, and multiply this out. So I'm going to leave the 3 over n still on the outside. Oh, I left my counters off. I equals 1 to n. Right, and this is just counting first rectangle, second rectangle, third rectangle, fourth rectangle, and so on. Times, what does this become? So that'll be 4 plus 6i over n, and then plus the 5. So 4 plus 5, that's 9, plus 6i over n. When you distribute the 2, right, that's 4 plus 6i over n, and then 4 plus 5 is 9. Let's take that 3 over n in now, and so I still have my limit, I still have my summation, and so I'm gonna have what now, 27 over n, 3, right, this is like over 1, so numerator times numerator, denominator times denominator, plus 3 over n times 6i over n, so I'm gonna get 18i over n squared. Same thing, numerator times numerator, denominator times denominator. And now we can, I'm going to use the properties of summations to split up the sum. So this is going to be the limit as n goes to infinity, and I'm going to have I equals 1 to n of 27 over n plus the summation I equals 1 to n of 18i over n squared. And so remember, our goal as we're simplifying the Riemann sum is to try to use these formulas. So identify when I see a summation I equals 1 to n and a constant, or summation of just I, or I square, or I cube, and try to isolate those, separate those, so that then I can use these formulas. The sum from I equals 1 to n of I is, this is the total sum, and so on. So here we're almost at the point where we can plug in our formulas, I think. Right, notice that this one doesn't have any I in its formula, it's just 27 over n. So 27 over n, you can consider that kind of like our constant, right? That's just a c. And then this, you can consider that also a constant times I. And so I'm just gonna rewrite it just slightly, just for to be clear here. So this is going to be, I'm going to leave it as 27 over n. This is just our c, our constant. There's no I, right? When you have the summation, the I is the thing that's changing. So I is the variable, n is a constant. Think about if you were writing a Riemann sum for something with 12 rectangles, right? Then n will be 12. So this will be 27 over 12. This will be 18 over 12 squared. So this will be constants, and the thing that's changing is really the I as you move from the first rectangle, the second rectangle, the third, until you get to the 12th rectangle. So that's what I mean by those are constants. The n is changing in the sense that we're taking the limit as n goes to infinity, but within the Riemann sum, the n is not changing. N is fixed. The I is the thing that's changing, or counter. So this one, I'm just going to write it slightly as 18 over n squared and then times I, so that I can see, oh, my summation of I, that's what I'm going to replace. Another way you can think of it is you can factor that 18 over n squared out of the summation. And so now we're ready to use our formulas. So when I have here, this is like saying the summation of C, right? I equals 1 to n of C, and this is n times C. So when I write this, I'm going to have my limit. I have not taken the limit, so I still have my limit notation there, and then it'll be n times C. So n times C, so 27 over n, plus my summation. And again, you can think about this as taking out the 18 over n squared. So this will be 18 over n squared times the summation, I equals 1 to n of just I. And so I can replace the summation with the formula. So this will be plus 18 over n squared times the summation of I, which is n times n plus 1 over 2. So it might be worthwhile to memorize those formulas that I wrote at the top of your notes, the useful formulas. And now let's simplify. So n divided by n, those cancel. So I have the limit as n goes to infinity of just 27, because those n's cancel, plus, and let's simplify the other one. And here I have n over n squared. Well, let me just leave it actually. So we'll have, when you multiply this n squared plus n, and you have the 18 on the outside, so it's going to be 18 n squared plus 18 n all over 2n squared. I guess we could have simplified the 18 and the 2 to be 9, but I'll just leave it like that. So as n goes to infinity, now I can take the limit. As n goes to infinity, what's happening here? So there's no n here, so I'm just going to have 27. And then plus, here I have a quadratic on the numerator and a quadratic on the denominator. So as n goes to infinity, the limit is going to be the ratio of the coefficients. So 18 over 2 is 9. So this is going to be, what does this give us? 36. So that is the area. Now this particular problem, we could have done it geometrically. If I graph the function 2x plus 5, that's a line with y-intercept at 5, and the slope is 2, so somewhat steep. Just bear with me as I try to draw this. Let me fix my y-intercept there. So when you're going from 2 to 5, so say that's 2 to 5, so you end up with this sort of trapezoid. And if you recall, the area of a trapezoid is, what is it, 1/2 b1 plus b2 times the height. So usually, like in this case, this will be, this oftentimes is for a trapezoid that looks more horizontal like that. So that's the height, and then you have your b1 and your b2, and so you do b1 plus b2 times height, and then divided by 2. So here, this is more like our height, right? Think of it this way. So this is 3, and then the height, our b1 or our b2 are going to be, this is going to be f of 2, and this is going to be f of 5. So the area for this particular trapezoid is 1/2 times b1 plus b2, so f of 2 plus f of 5 times the 3 here, and then we already have the 1/2 there. So our function is, that is 2x plus 5. So what is f of 2? Just plug in 2, so 2 times 2 is 4 plus 5, so 9, and then plus f of 5, 2 times 5 is 10 plus 5, 15, and then times 3. So what is this? this is going to give us 9 plus 15 and then times 3 and then divided by 2. So this gives us 36 as well. And so in this case we can do it geometrically because it was a nice line, but when you have something else like a parabola or some other curve, something that curves, then you can't do it geometrically. But this just kind of shows that, oh, okay, I can do it geometrically and see that the exact area is 36 and our integral, the Riemann sum, gives us the same thing. So I know that, oh, this is in fact true. The area under the curve represented by this integral and then evaluated by that Riemann sum does give me the exact area. So let's look at the next example. So I'm going to record in the next video the example for this one. So write a Riemann sum for the integral from 0 to 2 of 1 plus x cubed dx using left endpoints now. So this is a nice example because it's not a line. So when I draw the area under the curve and above the x-axis, it's not going to be a nice geometric shape, right? In this case we got a nice trapezoid, so we can do the area geometrically, but here we won't have that. So we'll see how we in fact really need to work the Riemann sum, and our goal in simplifying the Riemann sum is simplifying it enough so that we can use these formulas. So we're likely going to end up using that I equals 1 to n of I cubed, since I do have a 1 plus x cube in here, and using the left endpoints. All right, so go on to the next video if you want to see the work for this example.